Hi, my name is Justine Harkness, and in this video we'll look at how to rank changes in energy as we move charges through electric fields. The change in energy is directly proportional to both the force and the distance. And anytime I'm doing anything with physics, I always pay attention to my units. Energy itself has a unit of joules, and a joule is equal to a Newton meter. So if we think about energy and our change in energy, this would be proportional to something that has the units of newtons, which would be the force, and also something that has the units of meters, which would be the distance. So if in physics you ever get confused about what you're doing, one thing you can always rely on is the units. From this relationship between energy, force, and distance, we can derive the equation delta U, or our change in energy, is equal to the force multiplied by the distance. Now this formula is probably going to be familiar to you since this is the formula for work. And remember, one way that we can increase the energy of a system is to do work on that system. Now let's take a look at uniform electric fields and what that really means. Oftentimes when we're looking at a uniform electric field, we'll see that between two conducting plates, perhaps a capacitor, as you'll learn about in later videos. Now, the characteristic of a uniform electric field is that it is uniform. So if I have an electric field between these two plates that has a strength of 3 newtons per coulomb, what that means is at any point between these two plates, the electric field will be 3 newtons per coulomb. So it would be 3 newtons per coulomb here, it would be 3 newtons per coulomb over here, it would also be 3 newtons per coulomb over here. And because our electric field is constant, it will also exert a constant force on a charge. Remember that the force, our electrostatic force, is equal to the charge times the electric field. So if my electric field is constant, and I have the same charge placed anywhere, that means the force will also be constant on that charge anywhere we put it in this electric field. So let's take a look at some examples where we compare changes in energy as we go through uniform electric fields. So this question asks us to rank the change in energy of a +1 charge as it's moved through each of these electric fields. Now remember that the change in energy is proportional to both the force and the distance, and that the force is proportional to both the magnitude of the charge and the strength of the electric field. Now, since we are dealing with a +1 charge in all of these examples, what we really are going to be paying attention to for this question is the strength of the electric field, and then for the energy, the distance. Now, if we take a look at part A, here we have a field with a 1 Newton per coulomb strength, and we're moving this charge 1 unit. Now here we are moving the charge anti-parallel to the force, which would be applied by that electric field, so we would see a change in energy. And since it's 1 and 1, we'll just have a qualitative measure here of, in general, just 1 unit of change for our energy. Now looking at B, here we are moving this charge perpendicular to that electric field and perpendicular to that electric force. Since our motion is neither parallel nor anti-parallel to that electrostatic force, here there would be no change in the energy. In C, we have 2 newtons per coulomb and we're moving 1 unit. So since we have twice the field strength as we had in A, This would be a 2-unit change in energy. And in D, notice we have 1 Newton per coulomb, but we're moving it 2 units. So we have the same field strength as in A, but we're moving it twice the distance. So that would also give us twice the change in energy as we had in A. So this would be a 2-unit change in energy. Now to rank these, the lowest change in energy would of course go to what had no change. So B would be the lowest change in energy since, well, there wasn't any change in energy. After that comes A, since we had a 1-unit difference. And now notice C and D are tied. D had half of the electric field as C, but it was moved through twice the distance, and that's why those would have the same changes in energy. So now you should feel more comfortable ranking the change in energy as we move charges through electric fields.